Hi, I'm Manogna Ramireddy, and I want to explain about the project I made, which is malware classification with AWS SageMaker. First of all, I want to give an overview regarding the project. The report is all about how I built a smart computer program to help find bad software and malware. Malware is like a virus for computers. It can do a lot of harm, like stealing the information and damaging the files. So it's super important to be able to spot it quickly before it causes any trouble. To do this, I used something called machine learning, which is like teaching a computer to think for itself. I also used a really powerful tool called AWS SageMaker, which helped me training my program to recognize different types of malware. I trained my program on a big collection of data called the EMBER 2018 dataset. This dataset has lots of information about different types of software, both good and bad. I taught my program to look at this data and learn the differences between normal software and malware. Then I tested my program to see how well it could tell the difference between the two, the software and the malware and the benign. And guess what? It did a really good job. It was able to spot malware with high accuracy, which is exactly what I wanted. But and using the latest technology, I can stay one step ahead of the cyber threats and keep our digital world secure. Um, in methodology for I'm sorry. In methodology for malware classification, several key steps are data processing, training, and model training workflow. I began by gathering data from the EMBER 2018 dataset, which contains details about different types of software files. Using this data, I trained my program to recognize malware by by trying out various machine learning techniques like random forest and deep learning. After fine-tuning my program for accuracy, I deployed it on AWS SageMaker, a cloud platform to handle real-time requests effectively. This allowed me to create a system that can quickly analyze files for malware and provide results to users simultaneously. If we can see the results, this is the result I got through my model, which I for the malware samples when I gave like 100 malware samples, I got true positive as 90 and false negative as 10. So the precision here is zero point 0.9 and recall is zero point 0.9. And for the benign samples, I gave 100 benign samples and 95 out of which are true negatives and 5 are false positives. So the precision here is 0.95 and recall is 0.95. So um, I also mentioned the references I took and yeah, I also deployed a malware classification model capability of accuracy, and which is used for combating cyber threats and safeguarding digital assets. And this is the README file I made for the project. And this project is dedicated to combating the ever-growing threat of malware by deploying a sophisticated classification model using AWS SageMaker. The table of contents I used here is introduction, setup, deploy model on SageMaker, model usage, performance evaluation, malware samples, and contribution guidelines. So here, I want to mention that trained on the extensive EMBER dataset, the model excels in accurately distinguishing between benign and malware executing executable files. Then, by bolstering cybersecurity defenses, by harnessing the power of machine learning, it offers a robust and scalable solution for detecting and mitigating cyber threats. The deployment of this model as an API endpoint on SageMaker ensures seamless integration into existing systems, providing reliability and scalability in malware classification tasks. And I also provide how to make the setup and what dependencies need to be installed. And I provided my Git clone link here for and my code is in the GitHub. And I also mentioned like deployment model and which I did through the IPYNB file, and that also I mentioned here. And here with the Python client provided for ease of usage, extracting features and obtaining classification results becomes streamlined and efficient. The performance evaluation results impressive precision and recall rates are shown here, and it is good in detecting malware across diverse samples, and the samples and their detection is provided here. So in this file, I added what is malware classification, how to set up dependencies, how to deploy a model on SageMaker and its performance. So and this is the performance when we get like this performance when we get like 100 malware and 100 benign samples for detection. And I want to contribute from the community to enhance and improve my malware detection system further, whether it's optimizing algorithms, adding a new features, or refining any user interface, which are invaluable in fortifying my defenses against the cybersecurity. And the this is the requirements that I used for the project. I used Boto 3, and I also mentioned the versions of it. And Boto 3, the version I used is 1.18.63, which I used for Python to interact with the various AWS services. Similarly, I use like Pandas 1.3.3 for data manipulation and analysis, and it is used to clean and pre-process the data that we get, and perform several aggregations. And I used NumPy 1.2 to 1.2, which is a fundamental library for numerical computations and calculations for data, arrays, data structures, and all these things. For computations, I use NumPy. And I use scikit-learn, which is the version is 0.24.2, and this is just a go-to library for machine learning tasks. And I also use this requests 2.26.0. And this request is used for making HTTP requests in Python. And so that we can get the additional information which is fetched from external APIs. And I used SciPy 1.7.1, which is a kind of extension for SciPy, for NumPy, and companion library to NumPy, and provides additional functionality for scientific computing. Used its statistical functions, like optimizing and integrating routines for more advanced analytic tasks. And so this is the EMBER testing, and uh, this code prepares a data set for training a static malware detector. It iterates over two directories containing benign and malware samples, assigned labels 0 and 1, respectively. For each file in the directories, it constructs file path, adds it to the list of the samples, and assigns the corresponding labels to the label list. This process ensures that each sample is associated with the appropriate label for supervised learning. And this script clones a GitHub repository containing a dataset named uh, Dike dataset, which we can see here, and then proceeds to copy the first 100 benign and malware files from their respective directories within the dataset to separate the destination the directories named benign and malware under the directory content slash random samples. This process carried out using the shuttle.copy file function ensures that the specified files are duplicated from the source from the destination directories, which we can see like here. And I install the relative directories. And from the collections, I printed the n-gram and the 2-gram. So this is the trained data set which I got I did like earlier from malware. And here we are training the model, and we can see the versions, or like what the versions we used here. And and we can see the accuracy, recall, and F1 score. And so this is the EMBER testing. The We get all these accurate results from testing the data, and from the Python client. So the provided Python client defines function to simulate scanning files for malware and testing. The malware detection function using predefined file paths. We generally use Python files so that it checks if a file path contains a string malware or to simulate malware detection. The purpose of Python client is provide a convenient interface for users to interact with the service or system implement in Python, facilitating automation, integration, and ease of use in various applications such as testing, deployment, or any like data processing. In this thing, Python client could be useful for integrating the malware detection functionality into larger systems or workflows, and interaction with the malware scanning capabilities from the Python based application. So this is the reason we use a Python client. And in this code snippet, the provided Python script defines the function scan underscore file, which we can see here, and to simulate the malware detection based on presence of the term malware in the file path. Another function, test malware detection. The testing malware detection. Test the detection function using predefined benign and malware file paths. Finally, the main function we see here blocks executes the block. This block executes the test function when the script is run readily, and we can see here it is detecting whether it's benign or malware, which is like we can get its success. So this is the way we can use the Python client. So this is the code which I built for building a static malware detector. And here in the first code, we can see that this code iterates through directories containing benign and malware samples, creating a list of file paths which I have given here and corresponding labels. It collects file paths from specific directories and assign labels 0 for benign and 1 for malware, organizing them into two lists, list of samples and labels, which we can see here. So this is the list of samples and this is the labels. And finally, it facilitates easy access to sample paths and their corresponding labels for further processing or analysis. So here I install the scikit-learn pfile and also NLTK for further things. And here I this is the course snippet for this course splits the dataset into training and testing sets, ensuring an even distribution of labels in both sets. It randomly selects sample from the list of samples and is a list of samples and their corresponding labels, allocating 33% of data, which we can see here. This test size is 33, and here this 33% of data for testing and the remaining 67% for training. The stratify parameter ensures that the portion of labels remains consistent between the training and testing sets, while the random state ensures the reproducibility, fixing the random seed, which is like 42%. And here this code, I install collections here. This code defines functions to extract features from binary files for malware classification, and I used like several file paths and read file, extract engrams, get imports, and all these things. So here, read file reads a binary file and returns its data, and here extract engram counts extracts an engram count from the binary files byte sequence, which is read by read file. And here we can see that get imports, and this retrieves the imported DLL names from a PE file. And here this engram is for to count the number of engrams, and it prints the most common engrams list here, and I printed this here. And here, this code snippet is used for training a static malware detector, and it prints the exception in just in case if we don't have that, like if in case there's a detection or in the static malware. And here, this imports corpus train. This is a list containing preprocessed imported DLL names from training PE, which I printed here. And here, this num section train is a list containing the number of sections in each training PE file. And similarly, we have like a section name train here, which is a list containing preprocessed section names from training PE files, which I printed over there. And I also did ngram feature list train and all the required label trains and for training data. And here, I also trained xtrain df and xtest df. Similarly, and I gave CSV files for that for reading the file. And here, I printed the CLF, the random forest classifier. These estimations, I printed all the estimators and model job library. And here, after training the accuracy, I got the accuracy 0.99, which is I feel it's a very good accuracy. And similarly, I generated the same exceptional file for ngram feature. Earlier, I did for ngram count, and now I did for ngram feature. And this is the label train, and this is the label train, and here, yeah. So this snippet which I used here, um, yeah, this is the one. This code snippet imports the S3F library and creates an instance for the S3 file system class. It defines local and S3 paths for file transfer. Using the put method, it recursively uploads file from the local directories specified by local path, which I have given the local path here. Um, and it also um, local path here, and also I use the S3 bucket, which I use under the path of S3 path. And here, when we see the confusion matrix which I printed here, it has like the true labels and the predicted labels, and it shows the amount of true label and the predicted label, which is like 92 and 142, which I'm showing here. And other than this, this code initializes a SageMaker session and defines the executable role required for model deployment. And this code snippet creates a SageMaker sklearn model object, which is for model for deploying a machine learning model. And this model is specified by model data and artifact containing the trained model data. And similarly here, this code uh, ensuring the accessibility for SageMaker. Finally, it creates a SageMaker sklearn model object name model with the specified parameters for the deployment, such as like entry point script, that is interference.py, and framework and the framework version I used here is 0.20.0, ensuring the compatibility and seamless deployment.